This video is on triangle theorems and the properties, definitions, postulates, and theorems that can be used when writing proofs of when proving triangles are congruent. The first property is called the reflexive property. Reflexive property is when the triangles, the two triangles that you have an angle or a side in common. When the two triangles share an entire side, or when they share an entire angle, then those two that part that they are sharing is actually marked congruent. So as you can see here, they are sharing this side of HJ. That means that this segment HJ for the triangle KHJ and for IHJ, HJ has to be congruent to itself. So we would say that HJ is congruent to segment HJ by the reflexive property. This is used a lot whenever you see triangles attached to each other like this, especially if they share the entire side and there are no gaps. You can automatically mark those congruent because of the reflexive property. It's a property, so it has to be true. The second one is vertical angles are congruent. Vertical angles is a theorem. Vertical angles are when you have the two opposite rays are connecting and the angles that are formed. So when two lines are intersecting, you see how they form the letter X? Then the angles opposite of each other are congruent to each other. If we have this part right here where we form an X, we can say that the angles inside here are congruent. Now, these angles are congruent as well, but they are not inside the triangle, so they are not helpful to us. But these two angles right here, this angle and this angle, are inside the triangle. So marking these as congruent would be beneficial. Naming them is also important. We have to name them using your vertex of C in the middle. Now I'm going to name it angle ACB is congruent to angle. Now A actually corresponds to angle D on the other triangle. If I were to keep going, it'd be angle D. So it's congruent to angle DCE. And you can see that angle B and angle E would go together. The way you name things is really important when you're naming angles and segments because they have to match. They have to correspond to each other. The next one is a theorem. It's called the right angle theorem, or the right angles are congruent. This states that when you're given right triangles and or a square or rectangle, you know that the right angles are congruent. You actually have to state that the angles are congruent in a proof. Because if you just say they're right angles, that doesn't tell us congruency. And when you're proving triangles are congruent, the parts have to be congruent. So we can say that angle CBA is congruent to angle, so C goes along with D, B goes along with E, and A goes with A. So these two angles are congruent by the right angle theorem. We would say that these two angles are congruent because of the right angle theorem. The next one we'll use are the alternate interior angles of parallel lines are congruent. We'll also use corresponding angles. These two are used quite a bit when you have parallel lines. If you see basically the letter Z in your triangles, you'll end up having the alternate interior angles. So the interior angles, alternate interior angles, are congruent. And if you see the letter, basically it looks like a letter F, it could be a backwards F or upside down, but it looks kind of like an F, then the corners of the F will be congruent because of corresponding angles. So in this case, we have the letter Z because of the parallel lines. These parts right here will be the parallel parts. So on the Z, the same thing here. You'd have the parallel parts are the horizontals. So we have the parallel, and then we have that transversal, which forms the letter Z. So these two angles are congruent because of alternate interior angles. And we would name this as angle FGO, FGJ, I believe that's a J, is congruent to angle HJG. You have to be careful in naming those angles. The next one is the definition of a segment bisector. What that means is it results in two segments being congruent. It says that line L bisects segment TR. What that means is you want to underline the word bisect so you know what's happening, but then circle the next part because that tells you what is being bisected. When you circle the TR, that's what you focus on. You go to TR. TR is being cut in half. TR is being cut in half. So I can cut TR into two congruent sections. So what we would say is that segment TQ is congruent to segment RQ because of the definition of a segment bisector. We don't say the word midpoint. If we see the word bisect, we use the word bisect. So this part, right after bisect, whatever it says bisects, and then you circle the next part, that is what you look at. That is what you focus on. Specifically that. So look at TR. If you need to, you can highlight it and say this is what you're focusing on. That is what's being cut in half because of the bisect. Now that is slightly different than definition of midpoint. If it gives you that you have a midpoint, you must use the word midpoint. You cannot change the words around. It still results in two segments being congruent, but it's because of the midpoint. So again, we're going to underline the word, so midpoint of, and then we're going to circle the next parts, KI, segment KI. So I'm going to highlight all of KI because it says that J is the midpoint. So since J is the midpoint, midpoint cuts something in half as well. It results in these two congruent segments. So I can cut this in half because J is in the middle. So I can say that these two segments are congruent. So we can say that segment KJ is congruent to segment, we would say IJ. Because K and I correspond to each other, and J would correspond to itself. And this would be because of the definition of midpoint, because we have the word midpoint. Now, just like with the definition of segment bisector and midpoint, we have to make sure we understand what is happening here. It's called definition of an angle bisector. So on here we have segment HP bisects angle BPF. So again, we're going to underline the word bisects and then circle the next part. So we're going to specifically look at angle BPF. So I'm going to highlight angle BPF. So this angle right here. This is really what we want to focus on. That angle is being bisected. We don't have congruent sides. You see how it says an angle right there? If it says angle bisect, if it's an angle with it, we're going to have angles are congruent. So this angle, this big angle up here, is actually be cut into two parts. So we're actually going to mark it as two different angles. This little angle and this little angle, because these both form that big angle. So we could say that angle BPH, because it has to come down, is congruent to angle FPH. Again, it has to come down, so F to P to H. Because of the definition of angle bisector. Again, if it says angle bisector, you're going to have angles congruent. If it says segment bisector, you're going to have segments congruent. This next one, it says definition of perpendicular bisector. This actually gives you two different things. So I'm going to talk about if it says just definition of perpendicular, and then it also says definition of bisector. We've talked about the segment bisector and the angle bisector. So you actually have that bisector part comes from these two already. So I really want to talk about the definition of perpendicular. So the definition of the perpendicular aspect. So I'm going to highlight that in yellow because I want to focus on the perpendicular part. What does that result in? So the definition of perpendicular bisector results in two congruent segments and right angles. I want to focus specifically on perpendicular. Does perpendicular result in the two congruent segments or the right angles? Bisector, we know, gives us two congruent things. So bisector will be the two congruent segments. Perpendicular will give us right angles. So the perpendicular part tells us that we'll have right angles. If we know that this segment is perpendicular to the base, we can then say that these angles are right angles. We could say angle blank and angle blank are right angles. And we can say because of the definition of perpendicular, not because of the bisect part, but because of perpendicular. If we then say if we have a bisector, it will cut things in half, and we could say because of the definition of bisector. But if we have right angles, then we can go to this one and say that those right angles are now congruent. You actually have to say this before you can say this one. You have to be able to do 8, the perpendicular part, before you can do 3. The last one is the third angle theorem. This is not used as often. If you know two angles of a triangle are already congruent to two angles of another triangle, then the third angles are congruent. So if we already know that these two angles are congruent to those two angles, these two have to be congruent because they all have to add up to 180, and these are the same, so these also have to add up to 180. We don't use this one as often, but you can. It's not necessarily always needed. Now, do not assume anything if it is not in the given. You will be given information, and if it's not in that given, you cannot assume anything. Don't say, well, it looks like they're parallel, it looks like it's congruent, it looks like they're perpendicular. It does not matter. If it does not say something, or it does not follow one of these properties, or theorems, or definitions, or postulates, then you cannot use it. Do not assume anything if it is not in the given. You have to prove it. The most common that you're going to use are actually, it's going to be 1 through 7 and the perpendicular of 8. So 1 through 7 are most commonly used. 1 through 7 are most commonly used. With the perpendicular of 8. So they like to use the perpendicular part so that you have to prove that the right angles are congruent. Especially if you see it looks like a square, you have to, if it doesn't say that the angles are right angles, you have to prove it. So if it says in the given if it says a word in the given, it's generally going to be, you're going to say the definition of that word. So if you see the symbol for perpendicular, if you see that symbol, that means that you have the definition of perpendicular. Then you can say that the right angles are congruent because of right angle theorem. You also want to know this one because this will lead to the definition of a right triangle. If you're given right angles, if you have right angles, you could prove one of two things. You could prove that the right angles are congruent. Right angles are congruent. Or you could prove that the triangles are right triangles. Triangles are right triangles by the definition of a right triangle. The reason we would want to do this is if we're proving HL. We would use right angles are congruent for anything else. This is specifically for HL because you have to have right triangles in order to have hypotenuse. So if you have right angles, which is why we want to know that part, so that you know that they are right angles, once you have this part of it, you could go to either the right angles are congruent because of the right angle theorem, or you would say that the triangle ABC and triangle DEF are right triangles because of the definition of right triangles. So this is why the perpendicular part is important.